There's this invisible structure that powers pretty much everything you do on a computer, from finding a single file to loading a web page. It's one of the most important ideas in all of computer science, and it's based on something really simple, a tree. So today, we're going to unpack what it is and why it's such a big deal. I mean, really think about it for a second. You hit search and boom, in a fraction of a second, your computer plucks one specific file out of literally millions. How does it do that? It's not magic, but it is an incredibly clever piece of engineering.
Well, the answer actually starts with something you already use every day, the good old file folder system on your desktop, right? You make a main folder, then you put subfolders inside that, and then files inside those. That intuitive structure, that hierarchy, that's the key to the whole thing.
In the world of computer science, we call this a tree data structure. It's not a physical thing, of course, but a way of logically storing information that looks just like a hierarchy. Each little piece of data is called a node, and the lines connecting them show how they're all related.
And you know what? The terminology is just perfect. The top-level folder, like your main drive, is called the root. Any subfolder that has more folders inside it is a node, and the actual files at the very end of the line, the ones with nothing inside them, we call those leaves. See? Root, nodes, and leaves. It's a perfect analogy.
Okay, but hold on a second. You might be thinking, this seems way too complicated. Why not just chuck everything into one giant list? And that's a totally fair question. But a simple list is missing the one crucial advantage that makes trees so incredibly powerful.
And the difference is absolutely massive. Trying to find something in a simple list is like looking for one specific word in a huge book by starting at page 1 and reading every single page. It takes forever. But a tree? That's like using the table of contents. You just jump straight to the right chapter, then to the right section, and you find what you need in a tiny fraction of the time.
And it's not just about being fast. Trees are also amazingly good at adding or removing data on the fly. They can grow and shrink as needed. And of course, they are just the natural, perfect way to store anything that's supposed to have a hierarchy.
All right, so theory is one thing, but let's talk about where these trees are actually hiding in plain sight. I guarantee you've already used dozens, maybe even hundreds, of them just today without even realizing it. Let's do a little quickfire round.
So you type a website into your browser, right? The domain name system, or DNS, uses this giant tree structure to instantly look up that name and find the server's real address. It's basically the entire internet's phone book, all organized as a tree.
And this web page right here, the one you're looking at, yep, it's a tree. Your browser reads all the code and builds something called a DOM tree to understand the page's structure. The header, the body, the text, the images, it's all just one big hierarchy.
And how about when a database needs to find your one customer record among billions of others in the blink of an eye? It uses these super specialized trees, called B-trees, to create indexes that make that kind of mind-bogglingly fast search possible.
Oh, and you know that autocomplete or predictive text on your phone or in a search bar? That's all powered by another special kind of tree called a trie, which is built specifically for one thing: ridiculously fast text lookups.
Okay, so we've established they're fast and they're literally everywhere. But what's the actual secret sauce here? What makes them so incredibly efficient? To get that, we need to look at probably the most famous type of tree in all of computing.
Meet the binary tree. The rule here is super simple. Every single node can have, at most, 2 children, one on the left and one on the right. That's it. But that simple little rule is what unlocks its unbelievable performance. Because with every step you take down the tree, you get to throw away half of all the remaining data.
Which brings us to this number, 20. What on earth could this number possibly mean?
This, right here, is the magic of what we call logarithmic time. In a well-organized binary search tree, it takes a maximum of just 20 steps, 20 little comparisons, to find any single item in a collection of over 1 million items. Just let that sink in. Instead of 1 million checks, you only need 20. That is just staggering efficiency.
So we've got this amazing structure. But how does a computer program actually, walk through it to find something? Well, there are 2 main strategies for exploring a tree.
First up is what's called a depth-first search. Imagine you're in a maze. This is like picking one path and following it all the way to the end, to a dead end, before you turn around and try another path. The other way is a breadth-first search. This is more like throwing a stone in a pond. You explore everything 1 step away, then everything 2 steps away, and so on, exploring level by level, like ripples spreading out. Different problems call for different approaches.
So here's the thing. While the basic idea of a tree is pretty straightforward, computer scientists have gotten really creative and built all sorts of specialized versions. You can think of them like different tools in a toolbox, each one perfectly engineered for a specific job. And really, this is just scratching the surface. You've got heaps for managing priorities in a system, the trees we mentioned for autocomplete, syntax trees that let compilers understand your code, decision trees that are fundamental to AI and machine learning, and of course the B trees that keep our databases fast. Each one is a powerful variation on a theme.
So, you see, the tree is so much more than just some concept from a computer science textbook. It's this deep, fundamental pattern for organizing information that really mirrors how we think and how a lot of the world is structured. It's the invisible, elegant, and incredibly powerful backbone of the technology we use every single day. So the only question left is, now that you know what to look for, where else are you going to spot them?